All right, ladies and gentlemen, this is chapter 13, page 842, statistics and probability. We're going to talk about statistics today. So that begs the question, is there a difference? Yes, there is a difference. What is the difference? So statistics is where we get information from studying a sample of the population. So we pull out a small sample of the population. We ask them questions. I think most recently, probably like COVID would be a great example. They pull out certain people, and even my husband was in a flu shot study. So they pulled a sample of the population. You either got the old flu shot or the new flu shot, which was an mRNA, like the COVID shot. Isn't that what they called it? And something different anyway. And so they pull this sample out, they run a study, and then they draw conclusions about the whole population. That's what statistics is. All right, you take information from a sample of people and you draw conclusions to the whole population. Probability is actually where you look at the population as a whole and draw conclusions to a sample of people. All right? So they are different. So we're going to talk about statistics today. So data gathered from a sample of people falls in one of two categories. So the data from the sample group it is either qualitative or quantitative. Qualitative is something like, what sport do you prefer? Baseball, gymnastics, or basketball? That's a quality, right? That's a qualitative type of thing. It's like a preference, right? What flavor ice cream do you like? What's your favorite fast food hamburger joint? Okay? That is all qualitative. With qualitative, we have categories. Like baseball, soccer, we have categories. With quantitative, it's numerical. We're really looking at numbers, like the age of people, the median age of people at Sequitur. Like we're looking at numbers, okay? Not categories. Do you see the difference? Or the height of the average woman. That's a quantitative concept. The height of the average male, the size of your foot, that's all quantitative. It's numerical. Do you see the difference between qualitative and quantitative? Make sense? If I have quantitative, it's either the quantity is either discrete or it is continuous. It's discrete or it's continuous. So another numerical would be like hours. Okay? Miles you drive. If it's discrete, then there's a minimum increment. I don't remember if I spelled that right. I think it's, minimum increment. If it is discrete. Okay, so there would be a minimum. All right, so this is so fuzzy here, because you would think height would be discrete, right? But when I brought Thomas to Pennington Biomedical Center to be a part of a study, they gave him a little gift card. Have you ever done that? I think there's a recent one out. Okay. Well, yeah, he was there for an hour, got a $50 whatever gift card. Done. It's the most pay he ever made at the age of 6 or 7. Yeah, he was very young. All right, so anyway, when they measure your height, it's like they measure you, and then you have to go to the side, then you have to stretch and move and stretch, and then you go measure again. They measure you like 3 times. And then they take the average of the heights. Isn't that strange? So, although we would think it's discrete, it's more like continuous in some means. But, okay, your book would say it's continuous. I'm going to say height is discrete because do we really go below inches typically when we're measuring height? No. Like, I don't say I'm 5'4" and whatever many centimeters, right? I mean, I just don't say that, right? It's not 4 1/3 of an inch, 4 1/16 of an inch, right? Okay, so I would say that is really discrete. Continuous is when there's no minimum increment. One is not coming to my brain right off the top of the bat, but it will in just a minute. We'll look at some. Okay. All right. So you understand the difference between quantitative and qualitative? Yes? All right. So then how do we display this data? Well, it's different if it's qualitative as opposed to if it's quantitative. We display the data differently. If it's qualitative, we have 3 options. We have a frequency table, which we'll look at in a minute. Okay, so a frequency table is like, let's suppose we said we have 3 sports. Let's pick baseball. Well, y'all are going to think that's basketball since the women just won. All right, we'll say basketball because that's my favorite sport as of last Sunday, which was just 2 days ago. We'll say it's basketball. Okay, cheer. Some of you are going to be like, that's not a sport. Well, I'm telling you it's a sport. Or soccer. We'll call it soccer. Okay, all right. So a frequency table would be like, all right, how many people are in this room? 2, 4, 6, 8, 10, 12. There's 12 of us, 12 total. How many out of these 3 would choose basketball? See, I told you I was going to say basketball. Come on. Okay, 2, 4, 6, 7. 7 out of 12. That's the frequency. 7 out of 12. Got it? So you do a frequency table. We do 7 out of 12. That's the frequency. Okay, well, let's go ahead and finish it. Cheer. You cannot vote twice. There's only 12 of us. The numerator must add up to 12. Cheer.
I'm going to cheer just because I don't like watching basketball or soccer.
Okay. Soccer. 1, 2, 3. Does that add up correctly? Okay, one person is missing.
I don't think we'll vote it.
I voted for basketball.
Oh, okay.
Okay, anyway, that's what we're saying. There we go. This would be a frequency table. You get it? It's a frequency table. Do y'all understand that?
Yes.
Okay. Good. It could be a bar graph. Yeah. Or we could represent it in a pie chart. Right? That's the ways we could represent it. Okay, here's what I want to make note of. Bar graph, the bars do not touch. All right, so if we had, there were 7 of us. That would have been 7, right? And then we had the lone cheer person. And then we had soccer. All right, that would be a bar graph.
You're making them look like the same size.
I'm sorry.
No.
Soccer
It
had
is not
4,
okay.
so.
Oh, it's below the 5. Yeah. There we go. There we go. Got it? That would be a bar chart. All right.
Rightfully so.
A pie chart.
I know this.
Okay, we need to calculate the central angles for a pie chart.
What is this?
Okay, so
7/.
12 times 360. What is that? What's 7 over 12 times 360?
210.
Is it 210? Okay, so it's more than half. All right, so this would be basketball. 1/12 out of 360 would be 30.
Just 30.
30. So we'll say that's cheer, and then the rest is soccer, right? So you look at central angles for pie charts. Got it? Here's the deal. Bar chart, bars do not touch. So then, how do we display quantitative data? Well, here's how we display it. Okay, I'm going to go back to the middle. We have graphs. It just depends. We could do this, you know, it looks like your standard graph. It could be like this. It could be like this. Graphs, got it? Graphs. That's the whole point, graphs. No. Okay, y'all have heard of this before. Stem plots. Stem plots. We can actually do it in our calculators.
Yeah, we did that in our calculators already.
Okay? And so you know what the stem plot is? It looks like that's one of them. Or it's a stem plot can look like
I don't know.
Oh, that's what I know.
Yeah, it's 12. Oh, wait. Yeah, those are fine. You just do the list.
right? This is like your stem and leaf plot. This is more just a stem plot, okay? And the last one is a histogram. Histogram is what you've seen on the ACT.
It's a bar graph that.
It's a bar graph that touches.
What is the difference?
What's the difference?
Okay. Okay, I really need to draw this here. Okay, because it's all about numbers. So this is probably 0 to 5. Then this is probably greater than 5, less than 10. And this is greater than 10, less than 15.
Oh, that makes sense.
Got it? Okay, the ACT did a weird one, if some of y'all remember it. It just gradually grew greater and greater because it always started at 0. They did a histogram where always, the ACT did this. I know some of you I've tutored remember this. It went to 20, 0 to 20. And then this next one was 0 to 40.
Oh, yes, I got that wrong.
Yeah, and then this was 0 to 60. Okay, that was the dumbest histogram I've ever seen. Oh,
You gotta censor that.
censor it. Bleep. Okay, there we go. Censored. That's how it works. Okay. All right. Correct.
It's gonna get taken down.
Yeah, nobody watches my videos. Nobody watches except you people. Okay. All right. So you got it? Makes sense? All right, let's work through the problems, the practice problems, the examples, All right. All right, so now we're going to decide in example 1, what type of data it is. So when we're deciding what type of data, we're either choosing qualitative or quantitative. Okay? And if it is quantitative, then we have to decide, is it discrete or continuous? Got it? Okay, I already gave this one away. The height of each player on a basketball team. It's quantitative. I call it discrete. Your textbook would call it continuous. Okay. The style of shoes worn by the students in the classroom? Qualitative. The number of people in each household in the United States?
Quantitative.
Is it discrete or continuous?
Discrete.
You cannot have less than one whole person.
Well,
Yes.
Even if you think less of them, they are still an entire physical human being.
I forgot.
Well, if they're
or
alive.
just literally like half a person.
That they are dead and they don't count.
Wow. What about the like athlete that's got like no legs?
Yeah.
They're still a whole person.
Define whole person.
Right. They're still an entire person. We would count them as one. Okay. I have some that are not in your book. What about the number of questions answered correctly on a true-false test?
Qualitative.
What? No, it's quantitative.
The number of questions is quantitative. Is it discrete or continuous? There's only two choices.
It's multiple choice. You can't.
It's discrete because every question is one question. It would count as one.
Unless you get perfect credit.
All right? There is a minimum increment of one. Okay. Now think about this. The weight of an animal in the zoo. The weight of an animal in the zoo. It's quantitative. I bet it's continuous because I bet as they're weighing those animals, there are very, very, very minimal, very minute increments. So I would say it was continuous. Okay. What about the blood type of the juniors at Sequitur? It's qualitative. That's correct. All right. So now we're going to look at qualitative. Example 2 is a frequency table. So when you think frequency table, we've got to be thinking qualitative data. Okay? All right, so look at example 2. It says a group of 30 people. So we have 30, right? We have 30 people. That's going to be my denominator in my frequency table. That's how big my sample is. That's how I know I'm doing statistics. We're going to take these 30 people and decide what all of America likes in ice cream. Great. Right. Yes. Okay, you just remember that when you hear statistics on TV. I always think, really? They didn't ask me. Okay. Well, maybe they did, but I deleted the email. Okay. Here we go. A group of 30 people were asked about ice cream. Their choices were vanilla, chocolate. All right, so here's the flavor. Here's the frequency table. The flavor is vanilla. I know. Vanilla, chocolate, butter, pecan, mint, chocolate chip. Okay? So it says create a table with frequencies and relative frequencies. Okay, everybody look. Shh. The frequency is how many people chose that. So 6 chose vanilla, 12 chose chocolate, 4 butter pecan, 8 mint chocolate chip. The relative frequency is the ratio. Yeah, so that's 6 out of 30, and you would simplify that. 12 out of 30, 4 out of 30, 8 out of 30. What must the sum of the relative frequencies be? 1. One whole number. Got it? So if on a test I said, I've seen this on the ACT as well. What is the relative frequency for butter pecan? Well, you could take all the other ones and subtract it from 1, right? Or add the numerators and take 30 minus that, right? Make sense? All right, so a relative frequency can be written as a ratio or as a percent. Either one is acceptable, or as a decimal. I probably don't see it written as a decimal very often. Typically, it is written as a ratio or as a percent. But now that I'm saying that, I do believe on the ACT one time it was written in decimal form. You just had to add them and subtract them from 1. Got it? But in most textbooks that I read, it's either a ratio or a percent. All right, look at example 3. They took that same information and drew a bar graph. So see how the bars don't touch. Bar graphs, bars don't touch. Bar graph, bars, histogram, bars touch. Quantitative. Qualitative is a bar graph. Bars don't touch. They don't touch because there's not this continuous measurement on the x-axis. What's on the x-axis is a category. That's why they don't touch. All right, so then you just draw the bar as high as the frequency. Make sense? And then look at example 4. The pie chart. You take the relative frequency multiply it by 360 to get your central angle. And that's how you graph that pie chart. Got it? Everybody good with qualitative? Yes? You know how to get that central angle if you have the pie chart, right? It's a sector. It's been since geometry since you've seen that. It's a sector. Okay. That's qualitative information, qualitative data that we take from a sample of people and we impute it to an entire population. We say what's ever true of this sample is true of the population at large. So to actually get an accurate statistics, your sample should be large and representative of the population, right? It shouldn't just be all white males. That would be problematic, right? It shouldn't be just people who live in Baton Rouge. That would be problematic unless you're finding a statistic about maybe Baton Rouge, right? You wouldn't impute it to the entire United States because we are not representative of the entire United States, right? You want something from a sample, you should include people from every part of the United States, every culture in the United States. Make sense? All right, now let's look at quantitative information. Think numbers. All right, the way we can represent them is graphs. Look at the graphs on the bottom of page 846. There are 4 options here. The first one is uniform. All right, that just means there's no variation. It stays the same. Okay, so a uniform quantitative data would be like,
How many hearts?
okay, how many hearts does an average human have? 1. It would stay 1, right? Or, I was trying to think of something more logical. That was great. That was great. Okay, what would probably be uniform would be the age of a child in kindergarten or the age of a child in 1st grade. Yeah, notice I didn't say high school or 10th grade, 11th grade, because that might be not so uniform. right? Make sense? That's uniform. Symmetric means that there's some point of symmetry such that the right looks exactly like the left. So here's your symmetry. All right, that would be my axis of symmetry. Every parabola has an axis of symmetry, right? Such that what is on the left looks identical to what is on the right. So it's evenly distributed about some maximum or minimum point, right, on the graph. Evenly distributed left and right. So there would be the same quantity to the left of that midpoint of the graph as there would be to the right. All right, skewed right. Skewed right means there's nobody on the right. All right, skewed right means that the distribution has a much lower frequency to the right than to the left. Got it? This is skewed right, hump on left. Skewed right, hump on left. Got it? Skewed right, the hump's on the left. It's just the opposite. All right, so this might be the age of the people in the elementary school over there. What are most of their ages? Very young, right? Right, very young. There's very few older people in that school. Make sense? That would be something like skewed right. The age of a person, the age of people in an elementary school. Got it? Does everybody understand that? Skewed right, hump on left. Guess what skewed left is?
No one on bump on right.
Yeah, bump on right. All right, that's skewed left. Got it? All right. This would be like the average age of a person retiring. Most of them are old, right?
Not old, not old.
Over six, yeah. Most of them are. Thank you. Okay.
It is kind of.
It's okay. I'm there, so it's okay that I said old. All right. All right, so let's think about this. Oh, this would also be, I wrote some examples in my book. The age that a person dies in the U.S. Typically, very few die young. Most people die old, right? Okay. The day of the week. Oh, the day of the week of a person's birthday that lives in the state of Louisiana. What do you think it would be?
Tuesday.
It would be uniform. I think as many people, I think the day of the birthday would be uniform. I think there's as many people that probably have a birthday on a Sunday, that have it on a Monday, that have it on Tuesday. That'd be uniform.
But it changes every year.
Correct. So I think it's uniform every year. Everybody's changes.
More years than it's not.
There we go. You can think that. Okay. It's okay. I am 100% okay with it. Symmetric. Symmetric would be the ACT scores.
Really?
100%. Yes. That's how they calculate what your score is.
Oh, I wish.
They do. The average is about 19 to 21. It changes. So if you've done ACT tutoring with me, I always had to look at the back to figure out what your score was because it changed with every ACT score. You know why? Because they use statistics. Yeah. In college, most of Thomas's classes are scored using this, statistics.
That happens to my cousin and they dropped her grade.
Yeah. Well, so yeah, well the high on one of his tests was a 77, the low was a 3, I think. And
Should the 77 get 100?
That's good.
so they decided, yeah, what your grade was because of this. That's why Thomas is always like, I want to be near the average. I'm just okay if I'm a near or above. So the last test he took, he made an He made an lower 80s, can't remember, lower
And these
80s.
are our future engineers. And I'm so confused.
Yes, they are. So, lower
I have to
80s.
take the classes like normal.
And the average was in like the mid 60s. So his low 80 was maybe a B plus, which he was very happy with. Very happy with. All right, let's move on. Example 5. Let's talk about the shape of the data. Shape of the data, example 5. All right, so we're thinking about the 4 given shapes, and you're going to tell me the shape of the data. All right? It's either uniform, symmetric, skewed right, skewed left. Tell me what it is. What would the shape be if we graphed the last digit of each number in the phone book?
Or uniform.
I think it'll be uniform. I think 0 is picked as many times as 1 is, as 2 is. What about the salaries of employees of a corporation?
Skewed left. No.
Skewed right.
Skewed right. Yeah, skewed right.
Skewed right, because most people make a lower salary than make a big salary.
Was that really like really big stuff?
Yeah.
Big money.
What about the age of retirement? Oh, I already gave this away. Age of retirement. Skewed left. What about the heights of adult women in the U.S.? It has to be symmetric, right? I think there's an average height, and there's probably as many shorter as there are taller.
Probably more shorter.
You think there's more shorter? I know so many tall women.
Yeah, but if there's a ton of,
I know so many tall women.
if there was a bunch like that,
My sister is
more than
5'6".
18.
She's tall. Taller than you.
Okay, all right, let's move on. Look at the stem plot. Everybody look at the stem plot. You see that list of numbers? It's just at the bottom of page 847. You see those lists of numbers, 32, 67, 89, 90. You see all those numbers? Okay, they've made a stem plot.
32.
What goes to the left of that line is the tens place. What goes to the right is every one's digit, even if it's repeated. Even if it's repeated. So you do repeat numbers if it's repeated. You got it? And then look what happens if you put the stem plot to the side. Well, they've drawn the image there. If you rotate it 90 degrees, put it on its side, or just turn your book 90 degrees, you can see that that data would be skewed
Left.
left. You see that? Everybody see that? All right, so look at example 6. It's a stem plot. They've done it for you. Okay, except here we have decimal numbers. Here's the deal, ladies and gentlemen. The only number that goes to the right of the line is the last digit. If there are hundreds, if the numbers are in hundreds, the hundreds and the tens digit would go to the left of the line. Only the units digit or the last digit would go to the right. You understand what I'm saying? Yes? Yes.
If it was like 126, the 1 and 2 would be
Left, and the 6 would be right. Correct. There's only one digit that goes to the right. Got it? Everybody understand that? All right, that's example 6. You can see it. Then example 7. They draw a histogram. Create a histogram. Okay, there's a lot of numbers there. I would never give you that many numbers on a test. I would die if I had to do that many numbers. But look, they've already done it for you on the next page. They've drawn the histogram. Got it? So that the first range is 150 to 200. There's nobody from 200 to 250. There's about the same number of people from 250 to 300. Remember I told you on the ACT what they did? They started back at 0. So Yes, it grew and grew and grew. I've only seen it one time on the ACT, but I can't tell you a person that I've tutored that saw that the first time. So that's why I tell you, right? Look at the x-axis. Make sure that histogram is make sure you're aware of what it's counting by, right? And is it going back to the beginning? Okay.